Okay, picking up where we just left off, we're talking about hybrid orbitals. We can blend our atomic orbitals, s, p, d, f. We can put multiple of those together, put them in our blender, and boom, out pops a valence shell electron repulsion theory shape. So linear, trigonal planar, tetrahedral, trigonal bipyramidal, tetrahedral, those are our no lone pair electron groups. Those are the shapes that our electrons or electron geometries can form for our hybrid orbitals. sp3, we've got 1s and 3p orbitals that we blended together for a total of 4 orbitals. And so that means that we have 4 hybrid sp3 orbitals. And if we have 4 electron groups, that is the tetrahedral geometry. And so that's why we have tetrahedral shape for our sp3 hybrid orbitals that we combined there. For that carbon that we were looking at earlier, it only had 2 unfilled p orbitals, and it had 1 empty one. So we would have predicted that it would form 2 bonds. But if we blend our sp3 orbitals together to that sp3, then we've got 4 unfilled orbitals. And this agrees with what we expect based on what we know about carbon. Carbon likes to form 4 bonds, and the reason that it likes to form 4 bonds is because it can blend those s and 3p orbitals together to form the sp3 hybrid orbitals. We get 4 unfilled orbitals, means we can form 4 bonds. And so what we're seeing in this image is we've got our sp3 hybrid orbitals for our carbon. We have the 1s orbitals for our hydrogen. That's why they're just round shapes, because we're assuming that our terminal atoms are not hybridized. So this agrees with what we expect based on VSEPR, or Vsepar theory. Another thing that's cool about our hybridization is that we can accommodate a lone pair. So in NH3 ammonia, our Lewis structure would look like this. Nitrogen is also going to hybridize to form sp3 orbitals. The hydrogens will each bond, and this unbonded lobe, that would be the up direction, the z direction, can accommodate that lone pair. So this also predicts tetrahedral electron geometry as well as trigonal pyramidal molecular geometry. Okay, checking in to see if we've been paying attention. How many sp3 hybrid orbitals result from the hybridization of 1s and 3p orbitals? Number in equals number out. We put 4 in, we get 4 out. So we would have 4 sp3 hybrid orbitals. What would we call it if we blended 1s orbital and 2 p orbitals? Any ideas? If sp3 is 1s and 3p orbitals, what do we call 1s and 2p orbitals? The hybrid orbital shape. Yeah, sp2. So we can get 3 sp2 hybrid orbitals if we blend 1s and 2p orbitals together. We will be left with 1 unhybridized p orbital. So here's what that looks like. In this case, we're blending our s orbital with our px and our py orbitals. I don't know why they chose to draw the py that way, because z is usually up and down. But nonetheless, we blend these three things together. If we have three electron groups, that would be the trigonal planar geometry, and that's the form that our sp2 hybrid orbitals take on. When we do sp2 hybridization, we can also form double bonds. We'll see what that looks like in a bit. So for H2CO, formate, formaldehyde. Anyway, H2CO has sp2 hybrid orbitals. The carbon can form 4 bonds. It takes its normal 2s, 2p, blends it to sp2, and we've got the one left over p. So our hybrid sp2 orbitals, and again, they're all just one electron. So we've got the possibility for 4 bonds. Our hydrogens, both of them can bond. Our oxygen has 2 unfilled orbitals. And so that can interact with the sp2 and also the unhybridized p. What this looks like is this wonky thing. So what you're looking at is this green plane. It's a flat surface, just showing that our hydrogens are in the plane. So that's our trigonal planar. We've made it flat. And then coming up perpendicular to that is our p orbitals. So our carbon has the p orbital that's unhybridized, that's up and down. And our oxygen also has an unhybridized p orbital that's up and down. It is also getting a bond between its p orbital and the sp2 orbital. And so what some people might find funny, we've got, of course, an sp2 p bond, and we also have a p bond. So p orbital interacting with another p orbital to bond. The sigma and the pi we'll explain shortly, but this is what is happening. Why is it a p orbital that's interacting with the sp2 hybrid orbital? Because that's what's unfilled for oxygen, rather than having an s orbital interaction. Because our hydrogens are interacting with their s orbitals, because that's what's unfilled. So we have to think about what unfilled orbitals we have access to figure out how our interactions are going to occur. And the combination of this sp2p bond and the p to p bond is what makes our double bond. So we've got 2 types of bonds. We've got a pi bond, results when we get 2 p orbitals that overlap. And they overlap side by side because they're both sticking up and down. They're not interacting directly. So they form this weird vampire denture looking shape. And we also have a sigma bond that's caused by direct overlap of the bonds. In the parentheses is the Greek lowercase letters for pi and sigma. All of our single bonds are going to be sigma bonds. Our pi bonds can occur for double and triple bonds. So we can label the way that the bonds form, like I did earlier. The p orbital from the carbon, that's the one unhybridized orbital, and the p bond, or the p orbital from the oxygen, can overlap with that pi bond, where they're just next to each other. And they also have the direct overlap between the sp squared, or the sp2, from the carbon, that's the hybrid orbital, and the p orbital from the oxygen. Together, these two types of bonds form the double bond. Please let me know if you have questions or if you're confused. So valence bond theory, that's our new bond theory, gives us a little bit more information than just the Lewis model. In the Lewis model, we're just sharing two pairs of electrons. In valence bond theory, we have different types of bonds. Instead of those two identical bonds. We also got a visualization of how they're overlapping, so the direct overlap. That's our regular bond. And we also had that side-by-side overlap. And that side-by-side overlap is not going to be as good as the end-to-end overlap. Right? So our sigma bonds, because we're directly overlapping the orbitals, those are going to be stronger bonds than just smushing two things together sideways with our p orbital overlap. So this explains why our pi bond is not as strong. And where this shows up is if we look at bond strength, which will be, I guess, in 2 slides, or a couple of slides. Another takeaway, another thing that we learned from this, are single bonds. If we have our sp3 hybridization, we have end-to-end overlap, and so those can spin without changing anything. When we have a sigma bond and a pi bond, since those pi bonds are overlapping side by side, if you try to twist it, you would break that overlap. Doing like little doggy paddle thing with my hands so you can see that. So you cannot rotate on a double bond. Whereas for all these single bonds, these things can all be twisting around. So the Lewis structure that we have for dichloroethane, the 2 chlorines are in the down position. We could easily put the chlorine in the up or the side position. Those would be interchangeable forms because we can rotate around all of these sigma bonds. In our dichloroethene, we've got the double bond, so it's ene for the ending. These chlorines are locked in their positions. They are in the down position. They're on the same side together. We could flip it top and bottom so they'd both be on the top, but we would not be able to write one down and one up, because that would indicate that there had been a rotation that occurred. So this is a distinct molecule from if we swapped things. So that shape that I just drew, this is a distinctly different chemical than the Lewis structure that was provided. And you can actually buy these separately. I would assume that you can buy them separately. Typically, you can buy separate molecules like that. So this is what I was saying. We get free rotation, and so we can swap up and down and side. They can be wherever they want to. But when we have this double bond, that locks our rotation. And the way that shows up in our nomenclature is that we have cis, meaning that they're on the same side, and trans, meaning that they're on the opposite side. If we're just talking about 1,2-dichloroethene, the 1,2 just means that they're on different carbons. 1,2-dichloroethene could refer to either of these. If we use the cis or the trans in front, then that means specifically we're talking about them being on the same side or being on opposite sides. Another place where we see cis and trans show up is fatty acids. Unsaturated fatty acids. The unsaturated means that we've got some double bonds in there. And the cis-trans means that we've got either the carbon chain continuing on the same side or we've got it continuing on opposite sides. So this is what people are talking about when they're trying to scare you about fatty acids and unsaturated fats and stuff. That's what they mean by cis and trans. Okay, in a previous section, we learned double bonds are shorter and stronger than single bonds. A carbon-carbon single bond has an average bond energy of 347 kilojoules per mole. A carbon-carbon double bond has an average bond energy of 611 kilojoules per mole. According to valence bond theory, why is the double bond not just twice as strong as a single bond? AKA, why is it less than double the strength? Yeah, it's A. Our double bond is two different types of bonds. We have the sigma bond where it's direct overlap of the orbitals, and that's strong. And then our second bond that we add on top of that is the pi bond. They don't have complete overlap. They're just sitting next to each other. And since they don't have as much overlap, it's not as strong of a bond. Since it's not as strong of a bond, that's why it's less than double the strength. We can also form sp hybridizations and triple bonds. So when we do an sp hybridization, it's one s orbital, one p orbital. We get two sp hybrid orbitals, and we have two unhybridized p orbitals. So just regular dumbbells plus our sp hybrid orbital. Any guesses about what the sp orbital's shape is? It's linear. So when we combine our sp orbitals, we've got two orbitals. The electron geometry that works for two electron groups is linear. So we've got these, they look kind of like bowling pins. We've got two bowling pins, and if we draw them together, it's the linear shape. Right, so we've already learned what the hyperorbital shape is going to look like because we have the electron and molecular geometry knowledge from earlier. So let's draw a Lewis structure for acetylene. It's just this. Acetylene has sp hybrid orbitals. We know it has hybrid orbitals because the carbon's bonded to two things. It's bonded to the hydrogen, it's bonded to the other carbon. And since it's symmetrical, both carbons have the same hybridization. So we have the sp orbitals, and we have two p orbitals that are also unfilled. So we can still form 4 bonds. Our hydrogen can interact with 1. Our other carbon is also going to have the same hybridization. So the other sp can interact with that. This one would be bonded with the hydrogen. And then the 2p orbitals that are unhybridized, regular double shapes, those can also interact. And what we get is a triple bond. And this kind of looks like a bounce house to me. I don't know why. Our triple bond, though, consists of the sigma bond. So each of our carbons has that sp hybridization. One of those is going to bond with the hydrogen. The other is going to bond with the carbon. And then we've got the one set of p orbitals perpendicular to that in the up direction that we see along the top here and along the bottom. That's one set of p orbitals. And those are overlapping. We also have other ones that are 90 degrees to those that are overlapping. So we've got an additional 2 p2p bonds. That forms our second and third bonds on top of that sigma. What is the hybridization of carbon in CO2? Our Lewis structure is what we would want to start with. We would draw that out. It would look like this. We'd say, oh no, carbon doesn't have enough electrons, so we dump some of these lone pairs in to form double bonds. And it would end up looking like that for our Lewis structure. How many bonds, how many things is carbon bonded to? Carbon's bonded to 2 things. So it needs sp for its hybridization. What if we did sp3 hybridization? How would these bond? How would we form double bonds with an sp3 hybridization? So remember our sp3, right, we would have our tetrahedral geometry. Those would be our 3 orbitals. We would have to use 2 of these, let's say an arm and a leg, to bond to the carbons. That doesn't really work out for our predicted shape. And then we would somehow have to double bond with the other arm and the leg. That doesn't really work. I don't know a good way to show you that spatially. But if you think about how our double bonds have typically formed, if our carbon has sp hybridization and our oxygens have their unbonded p orbitals, they would also have one that's up, and this one I'm going to put in the back position. So our sigma bond is going to occur between the sp and one of the p of oxygen. The p because that's the unfilled orbital for the oxygen. This is what our orbital diagram looks like on the right here for oxygen. So we've got 2 p orbitals that can bond. One of those is going to be a direct overlap, the sigma. And then we can form that second bond by overlapping our pz orbitals on the right here. That's our second bond with the right oxygen. And for the left one, I'll do that in green, trying to draw it so that it looks like it's front back. That's going to overlap with another p orbital from the oxygen. So that's the only way that we can get 2 double bonds, is if we have the sp. So on the right, we've got this vertical overlap. On the left, we've got the flat overlap. But also you could get that it's sp hybridization because it's just bonded to 2 things, no lone pairs. If we had lone pairs, then we might need sp2 or sp3 hybridization to accommodate those lone pairs. So them's the basics. We can also incorporate d orbitals in our hybridization. In our Lewis theory model, this was what we called expanded octets. In valence bond theory, Those expanded octets are hybridization with d orbitals. So we can combine an s orbital, 3 d orbitals, and 1 d orbital. To get 5 sp3d hybrid orbitals. And this is the trigonal bipyramidal shape. So we've got our 3 equatorial positions, and we've got our 2 axial up and down positions. Here's what that might look like. So a Lewis structure between arsenic and 5 fluorines. We're going to form 5 bonds. We're not going to have any leftovers to use as lone groups or lone pairs on arsenic. Fluorine's unfilled orbital is a p orbital. So that's why we're using the p orbitals in this diagram. So we've got sigma overlap between our sp3d orbitals of our arsenic and the p orbital of our fluorine. And that gives us trigonal bipyramidal shape. We can also form 6 sp3d2 hybrid orbitals. And this has the octahedral geometry. Octahedral is our standard for 6 electron groups. So the way that we've got this drawn, we've got 2 axial and 4 equatorial. All of these positions are equal since it's all 90 degrees between each of the adjacent groups. So you can rotate that however you want. It doesn't really make a difference. We talked about that when we covered octahedral geometry. So if we have sulfur hexafluoride, again, fluorine's interacting with the p orbitals, we get sigma overlap between the 6 sp3d2 orbitals of our sulfur. Questions about any of our hybrid orbitals or the shapes that they form? Okay. So for writing our bonding schemes, if we wanted to be completely rigorous, then we would run simulations in a computer with a specific program to calculate the best hybrid orbital scenario. We're not going to do that. We're just going to guess based on the electron geometry of the interior atoms. And that's good enough for us. So our hybridizations have shapes, our electron geometries have shapes. Pick the shapes that are the same. Whatever hybridization you need to get the same shape as your electron geometry, that's the one we'll pick. There's probably other better, fancy ways of doing it, but matching shapes works. So if you have two electron groups, we would call that linear electron geometry, and our SP matches that electron geometry. You can also just match the number of electron groups to the number of hybrid orbitals. That works as well. You might use this table to do that. So our steps for doing hybridization and figuring out how the bonds are going. We're going to do our Lewis structure. Hopefully you're a pro at Lewis structures, or at least pretty good. Then we can predict the electron geometry about the interior atoms. We've got, 5 options? Linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Yeah, 5 options. And then you'll pick the correct hybridization for the interior atoms based on the electron geometry. Alternatively, number of electron groups matches number of hybrid orbitals. So for electron groups, we're definitely going to have S in there. We're going to have some number of P's next. We can get up to 3 P's. So sp3 will be 4 electron groups. So if we have 4 electron groups, we'll have 4 hybrid orbitals in our sp3, for example. And then you can sketch out your molecule using the whatever shapes you want. And keeping in mind the orbitals that are available. So for our terminal atoms, that's going to be based on unfilled orbitals. If you've got something like hydrogen, it only has access to the 1s orbital. That's going to be spherical. So it's going to be a spherical shape. If we're doing something like fluorine, chlorine, oxygen, we're going to have unfilled p orbitals. So we're going to draw dumbbell shapes instead. Then you can label the bonds using sigma, where we have direct overlap, or pi, where we have parallel or side-by-side overlap, like in our double and triple bonds. We want to do a hybridization and bonding scheme for xenon tetrafluoride, the first thing that we'll need to do is the Lewis structure. I'm assuming that we can all do the Lewis structure for this. So I'm just going to give it to you to save you the time. This should be the correct Lewis structure for xenon tetrafluoride. What hybridization are we going to have on xenon? Alternative question, how many electron groups do we have on xenon? Counting our bonds first, we have 1, 2, 3, 4, and we have 2 lone pairs. That makes 5 and 6. We have 6 electron groups. We need 6 hybrid orbitals. What's our hybridization going to be then? We're definitely going to need S. All of our hybrid orbitals have S in them. Next comes P. How many P orbitals can we put into a hybrid orbital? We can get up to 3. So we're up to 4. We need 2 more. That'll have to come from our D orbitals. So sp3d2, that's a total of 6 atomic orbitals in, 6 hybrid orbitals out. So that's our hybridization. What's our shape for sp3d2, or what's our shape for 6 electron groups? Octahedral, meaning we've got xenon in the middle. We're going to have two axial, 4 equatorial, all right, so that's going to be our shape. 1 up, 1 down, 4 out on the sides. Alternatively, and what might be easier here, is if we rotate this 90 degrees towards us. So we'd have 2 up to the sides, 2 down to the sides, 1 coming out, 1 going back. Something like that. Those are 2 ways that we can draw it. Another thing to consider when we're putting this together is where our groups go. We've got 4 fluorines and 2 lone pairs to place. How should we place them? If you've been memorizing your shapes, this one should come pretty quickly. We can also think about repulsions. What is our strongest repulsion? Lone pairs. So we want to minimize the amount that our lone pairs interact. All of these positions is 90 degrees from its next position. So how can we get our 2 lone pairs as far away from each other as possible? We put them on opposite sides. So in this left diagram, we would put one lone pair up, one lone pair down, or any other opposite combination. So the reason that I flipped it for this right one is so that we've got a lone pair coming out and a lone pair going away. And those will be empty. I'm going to draw on top of this our sp3d2 orbitals. The lone pairs are also in sp3d2 orbitals. And then in the plane of the board, we've got our 4 fluorines. With their p orbitals. So this is a sigma bond that is xenon sp3d2 with fluorine P, and all the bonds are the same. So that's sort of what you would expect to put together. Questions or confusions about that? It is kind of a hairy one to draw out. Okay, go ahead and give a try doing a hybridization and bonding scheme for HCN. So there's the Lewis structure for HCN. If you were confused about whether carbon or nitrogen goes in the middle, formal charges. We're memorizing it. Another way that you could come up with this, carbon in the middle instead of nitrogen, carbon likes to form 4 bonds, nitrogen likes to only form 3 bonds. Another thing that you kind of just pick up through practice. What hybridization then would we expect for carbon? How many electron groups does it have? A double bond and a triple bond count as 1 electron group. Carbon has 2 electron groups. That means we need 2 hybrid orbitals. So we get sp hybridization. That shape matches with our electron geometry. So we've got carbon in the middle, hydrogen on the side, we've got our sp hybridized orbitals. We can draw out an orbital diagram as well. What orbital is hydrogen bringing to the table? It's bringing s. It's got 1 unpaired electron in the 1s. Since it's bringing s, draw it in as a circle for its orbital, or a sphere. So our bond here, it's a sigma bond between, from hydrogen, an s orbital, and carbon with an sp orbital. On the other side, we have nitrogen. What orbitals is nitrogen bringing to the table for bonding? It's past the 2s on the periodic table. This 2s is filled. It's in the 3rd spot in the p block. So it's bringing 3 2p orbitals. I guess really these should overlap. So we've got sigma bonding between carbon's sp and nitrogen's p orbital. That's weird. So these two maybe match up in green there. The s orbital and one of our sps, that's a sigma bond. And also the other sp and one of those 2p's. And what do we do for the remaining 2p orbitals? How do those come into play? pi bonds. So in addition to what's drawn already, we can add in this vertical element. And we can add in, as best as I can, not being an art student, a set of pi bonds coming in and out of the board. So we've got our up position pi bonds. Those can overlap. We have our flat ones that are coming in and out of the board. Those can overlap. So we've got 2 pi bonds between the 2 p orbitals of carbon and nitrogen. So we would write a little pi symbol, carbon P, nitrogen P as our labels for those. Questions? I think we already did this one for CO2. We did hybridization and a bonding scheme for this. So I'm going to skip it. This was shown earlier. I think it wasn't shown in this exact context, but we did see it. If you've got questions about it, I'm happy to go over it with you. So that's about an hour. I think we'll stop there. We've got about 20 slides left. This is where it gets really hairy, at least for me. So this is a great place to stop. And I'll see if I can shave it a little bit before Wednesday.